All right, welcome everyone. So this is lecture 16. Okay. So first couple of announcements. I'll post exam two solutions by Monday. And the grades are delayed currently. The TAs are still part of the UAW strike. So and I'll try and grade them starting next week, but it's going to take time because we're missing 5 TAs completely. Okay. And okay, so that's all about the exam, and we'll figure out more logistics as I know more information. But for now, let's just focus on the content. Okay. All right. So last class we talked about Rice's theorem, and then we also kind of started having this discussion that Turing completeness, as good as it is, because it says that your language or your model is very powerful or as powerful as we expect to be possible in this physical universe, it can also be a bug, right? So we discussed this in the context of the Ethereum hack, where if you had a Turing complete language to code up some things, you can create programs which can do all kinds of stuff. In particular, you can steal $60 million, right? So the reason one can think of it as a bug is that if your language is Turing complete, then it becomes that much harder to reason about programs in your language. Okay. And as I keep saying, a large part of computing deals with analyzing and running other programs, right? If you're writing system software, programming languages software, you're building any kind of infrastructure, your input is going to be programmed. So you have to be able to reason about that, right? So to this end, we will take that as our cue for studying some other models where we're going to kind of tie our hands behind our back so that we can reason about some important tasks. Okay. And although this is not the only motivation for it, historically, they were very important for other reasons, as we will discuss. I think this is a pretty good motivation for many other settings. Okay. And the specific model that we're going to look at is what's called context-free grammars. Or CFGs. It's a very simple, elegant model. As far as models go, I think it's really beautiful in its elegance and also amazingly useful, as we will see. Okay. And just to kind of spoil the punchline, we will see that DFAs are kind of less powerful than CFGs, which are provably less powerful than Turing machines. All right. So CFGs are kind of some of these models which have intermediate complexity between finite automata and the all-powerful Turing machines. Okay. All right. So what are context-free grammars? So you can define them. I'll first kind of list some things to formally state what they are, and then we will kind of identify their definition just by examples. That's the best way to illustrate what they are. So what are CFGs, context-free grammars? So these are things which are specified by a collection of things. You have variables, you have something called the alphabet. Okay, and then you have something called rules, and then you have something called a start symbol. Okay, so I'll just spell all of this out and then we'll look at an example. So these are variables. These are alphabet, sometimes also called terminals. Okay, and you also have rules Finally, you also have what are called start variables. All right. And so we should definitely think that sigma is disjoint from variables. Okay. So you have a collection of variables, typically we'll denote them with English alphabet, and the alphabet or terminals will denote with like, zeros and ones and small letters. Okay. And, actually I just noticed that there's only one person with video on. If you can, please turn it on. It makes me feel better for sure, instead of just talking into blank pieces in the screen. That's very helpful to get some feedback and kind of, at least have some persons on the other side. Okay. All right. And as usual, if you have any questions, just please unmute yourself and ask away, and we'll take the discussion from there. All right. Okay. So as I said, we'll kind of illustrate with examples, right? So variables and sigma are kind of self-explanatory. These are, just like our typical variables, large alphabet. And then you have these letters. I see we have some people who are, and other species who are very eager to learn about CFGs. That's great to see. All right. We also have rules. Okay, so what is a rule? A rule is essentially kind of a substitution mechanism, right? So it says, if I have a variable like, let's say A, you can replace it with something else. Okay, you should think of this as a variable. And what you can replace it with is anything from it's a string. You can replace it not with a single symbol, but with any string, which is a union of alphabet and variables start. Okay, we'll look at an example to kind of make it concrete. So rules is a collection of, rules like this. You have a variable, a single variable on the left-hand side, that is important. And on the right-hand side, you have a string, which can have variables again, and some terminals mixed in. All right. So let's look at an example grammar to illustrate this. So example, I'll call this grammar G1. Okay. So there is only one variable. So recall, we always list the variables first, right? The alphabet, typically, again, in this class, we'll only stick to binary alphabets or 0-1 things, but you can always define it over other alphabet like English, all kinds of ASCII characters and so on. Then you have the rules, and the starting symbol, which typically has to be which is a variable always, is A. Okay, so we'll see what those mean. So this is a set of variables, terminals, rules, and the startings. But I haven't told you what the rules are. Let's look at some examples of what the rules are. Okay, so this is simple enough grammar. It has two rules. If you see an A, you can replace it with a 0 followed by a followed by a 1. Okay, or if you see an A, you can replace it with the empty string. Okay, meaning essentially you're kind of getting rid of it, right? So that's your first complete description of a grammar, right? You have variables, rules, everything specified. Okay, so okay, so I have some notation here, but what do you do with these things, right? So what you get to do with these things, and the most important operation in the context of grammars, or in the context of context-free grammars, are derivatives, or sorry, derivations. Okay, not calculus derivatives, but derivations. Okay, so basically it's some kind of relation which lets you go from one string to another string, right? So let's say I have alpha, which is from, it is a string which involves variables, terminals, all mixed together, some length. And you have another such string with variables, alphabet, all thrown in together. And we say alpha leads to beta, okay? And we often put a subscript G here, kind of to, if there, if you have different grammars that I'm dealing with, I would also put a G there to say, okay, this is the exact grammar you're dealing with. But typically, you can take it kind of, it'll be clear from what we're discussing. If like alpha can go to beta, or alpha leads to beta, or beta can be derived from alpha, all of this means the same thing in English. If we can get, it's a pretty natural definition, beta, by replacing a variable in alpha using a rule from R. Okay, so rule is just a set of rules for substitution, right? We'll say beta can be derived from alpha if there is some variable in alpha which you can replace with whatever is on the right hand side of a rule, and you get beta. Okay, so as an example, okay, so we have our grammar G1 above, and I want to say that let's say if I have A, okay, this definitely leads to the string 0A1, because I can replace A with 0A1. Okay, that's no surprise. But if I also have 0A, I can go to 00A1. That is also valid, right? I can just replace this A with this rule. Okay, and you have many other things like this. Let's say I have 00A1. This implies 000A11. Okay, again, just for highlighting, I'm kind of telling you what rule we are applying here. Okay, and you can also go to something like this. Okay, if I use the rule A to epsilon, then I immediately get a terminal string. And once I get a terminal string, kind of the derivation stop with it, right? In a derivation, you can only replace a variable with whatever was there in the rule. So if I have a string of terminals or alphabet, that's why they're called terminals, your derivations stop. Okay, and if I have, you can also have a string which is like this. This would also imply 0A1. Now, if I replace the first one here, A0. And you can also derive A0, A1, 0. Okay? Like, you have pretty much a lot of flexibility. As long as you can substitute any variable, that gives you a derivation. All right, any questions about this? Okay, so natural enough, I'm purposely illustrating all the confusing cases you can have. There's no order in which you have to substitute. Everything is a valid derivation. Okay, that's all good. But then the next important step is once okay, so can you explain the second derivation? So what I'm doing in the second derivation here is I'm replacing the second A with the rule A to 0A1. Right, that is completely valid. I can replace any variable with a rule that it is involved in. Okay, all right. So next, we can also chain these derivations together. Okay, so that's the second sort of important concept. And we will say, this is just my notation, like, implies star of G of beta if there exists a chain of, or a sequence, or let me say a chain a chain of derivations to get beta from alpha. Okay, and once again, we are really thinking of alpha and beta both being general strings at this point, right? They can involve any sequence of the terminals or the variables. Okay, and you can chain them. In other words, there exist some alpha 1, alpha 2, up to alpha L minus 1, such that you can go from alpha to alpha 1 with a single derivation. You can go from alpha 1 to alpha 2, you can go to alpha 3, and so on. And so on. Okay, until you actually see beta. Okay, so again, let's do an example. Let me kind of put this here for reference. Okay, so let's do an example. For grammar G1 above, I want to say that A can lead by multiple derivations to the string 00A11. Okay, so why is that? I can go from A with a single substitution, right? By applying the first rule to 0A1. Okay, and then I can apply the same rule again to get 00A11. Okay, and you can have more complicated things, right? I can say, this also holds. Okay, so this also holds. Why? Well, let's see. So I can go from AA to, I'll replace the first A to get 0A1A. Then I'll replace the first A again to get 00A11A. Okay, so let me identify which variable I'm replacing. I'll replace the first variable again to say 0, 0, 3 zeros, 1, 1, 1, A. Okay, and then I can again chain them, right? I can say this implies 0, 0, 1, 1, 1, A. Okay, now I'm applying a different rule here. I'm replacing A with the rule that takes you directly to epsilon, right? And then I can say I would get 0, 0, 1, 1, 0, A1. Okay, if I replace this guy. Okay. Any questions about this? Okay, so I can chain these things however which way I want. As long as I can chain for two things, connect them by a chain, I'll say one implies the other via the star relation under the grammar. Okay. Now we are ready to define some model of computation which comes from a grammar. Okay, it's kind of similar to how we define regular expressions, right? A grammar gives you a set of rules to generate sentences. Agree that English is not a very codifiable language this way, but you can easily imagine, okay, I write down a set of rules, and maybe you can generate every possible or every grammatically correct English sentence using these rules. It's not that simple, but you can imagine that being true for other languages. Okay, And that was one of the original motivations for context-free grammars, to try and define models for actual spoken languages and so on. Okay. So if this is an important definition, so we'll say if G is a grammar, okay, and I have a string of only terminals. Okay, so now I'm only looking at a terminal sequence. So you should always keep in mind that our target is to really derive a sequence of terminals from variables. Okay, we'll see a sequence of terminals is matched to or by, you can see both things, to G if, recall that G was this kind of, had variables, terminals, rules, and also a special symbol, special variable, which we designated as a start. Okay, we'll say a string of terminals is matched by the grammar or matched to the grammar if the start symbol can lead to this terminal sequence. So if the terminal sequence can be derived only from the start symbol, we'll say that the string X matches the grammar. Okay. And once we have this, we can also define the language of a grammar, which is all sequences of terminals which can be matched. All right. And you can also define a function corresponding to the grammar. These are all kind of really restating the same thing. We say the function of the grammar on any terminal sequence is 1 if X matches G and 0 otherwise. Okay, so we have a language generated by grammar G is LG. Okay, sometimes you also see language accepted. Okay, so both kind of mean the same thing, but for context-free grammars, you can think of it as a way of explicitly telling you how to generate valid sequences. Okay, that's where talking about generation kind of makes sense. All right. Any questions about this definition? Okay, so let's look at an example, right? And finally, just to add to some more sort of classical nomenclature. So just as we said, a function is regular, if there was a DFA computing it, if there was a regular expression which computes it, we say that a function f sigma star to 0, 1 is context free. Okay, if there exists a grammar G such that f of x is exactly the function computed by the grammar. Okay, and the language would be called context-free languages. Okay, so the languages generated by grammars, as here, are called context-free languages or CFLs, and we often abbreviate CF context-free grammars as CFGs. Okay, so there's a reason why they're called context-free. They're called context-free because somehow, when you're applying a rule, you look at a variable and immediately substitute with whatever is on the right-hand side, right? You never pay attention to what is around that variable, right? And what is around is kind of like context, right? And if I have, this dog is eating something, okay? Context-free grammar would let you replace dog with anything, irrespective of whether there is this dog or this and around. Okay. So let's look at an example. Let's look at the same example that we were doing to get some insight. All right, so where is our grammar? It's all the way here. Let's copy it. Let's try and compute what's the language generated, it's a function computed by this grammar. Okay, so let me ask you a question. What is the language generated by this grammar? Any guesses? So if I have only these two rules, my starting symbol is A, what kind of strings can I generate? Can I generate something like 0, 1, 0? Any suggestions or guesses? Yeah, exactly. So there are two guesses here. First one is 0 to the m, 1 to the m. The other is strings with equal number of zeros and ones. So it's not all strings with equal number of zeros and ones, because you never cross, a 1 with a 0. Okay. So it was actually just going to be something as simple as this. All right. And you can see it kind of visually. So basically, once every time we apply rule A20A1, we kind of add a 0 in front and a 1 after the symbol A, right? So we never let a 0 follow A, right? Zeros always go to the left of the symbol, ones always go to the right of the symbol. Okay. And once I apply this rule, A to epsilon, the derivations would stop because you would not be left with any variables. Okay. So for instance, like, you go from A to 0A1. Let's say you go to 00A11 and so on. So there's a very good question in the chat, which is, why can't we use the derivation AA to 0A1, 0A1? So that is a valid derivation, but when we look at the matching a string, we are specifying that you're only allowed to start from the starting symbol. Okay. You start from A, and whatever you can get to from there is what your language matches. So you never get to AA at all. So you never get to do 0A1, 0A1. Okay. And there's another question, which is, would you say 0 to the n, A, and 1 to the n also match the language? And the answer is no, because somehow we are only interested in this definition on strings with only terminals. Okay. It is definitely true that A can help you derive 0 to the n, A, 1 to the n. Okay. But in the language, just by definition, you're only looking at strings of terminals. So you have to get rid of all variables to get to a valid string in the language. Okay. Any questions? Does this clarify the questions that were already asked? Okay, let's look at some more examples. I think it's fun to play with these rules and grammars and see what kind of stuff you can get. Okay, and one thing you might notice is that context-free grammars are already doing something that regular languages, regular expressions, or DFS could not. Okay, so just to recall, we saw earlier that 0 to the n, 1 to the n is greater than or equal to 0 is not. Is there a question?
How long have you had it? Oh my God, you played it? You played?
Is not a regular language. Okay? It's not a regular language, but it is context free. You can generate it with context free grammar. All right. Okay. So let's look at one more example. I mean, we'll look at several examples. As I said, I like playing with these things. So let's say I have G2, which starts with, again, simple stuff. So we have a single variable, maybe two, the terminals are just zeros and ones. I have to tell you what the rules are. The starting variable is just A again. And this time we will have more rules. So I'll say A can be replaced with 0A0. A can be replaced with 1A1. You can replace A with 0. You can replace A with 1. And you can replace A with the empty symbol. Okay, so now you have 5 rules, right? A can go to 0A0, 1A1, and 0 or 1, the individual bits, or epsilon, right? So these are kind of your terminating derivations, right? Once I apply this, you get rid of the variable completely, okay? And every time you apply these rules, you're going to only have one variable, right? There's only one copy of A that you're adding. Okay, now what language does G2 generate? Okay, so what is the language that computes? I see several answers. It is actually palindromes. Okay, so you always only start with the start symbol, right? So LG is all X, such that X is a palindrome. Meaning X reads same from left to right and right to left. Okay, so why is that, right? The reason that happens is basically whenever we apply any of these rules, what we are doing is if I introduce a 0, I'm also introducing a 0 on the other side. Whenever I introduce a 1, I also introduce a 1 kind of exactly in the mirror copy. Okay. So for instance, I can say, let's say I do something like this, right? I go to 0A0, I can do 0, 1A, 1, 0 again, right? You can see every time I'm introducing something, I'm kind of matching it with something, the same bit on the other side, right? So you can go again to maybe 0, 1, 0, A, 0, 1, 0. Okay. And so on. Like, and if I do it G2, finally, I can maybe I'll just replace it with a 0. I get this guy. Okay. And often reasoning about grammars like this, at least for the ones that we are stating explicitly, comes down to like, trying a few examples and seeing what happens, right? Really understand the mechanism here. Every time we create a 0, we're kind of creating a mirror image 0 on the other side. So that's why you get palindromes. Okay. Any questions about this? Okay. And one thing, so if you look at this, the way we are writing it, we have 5 rules, and writing that is kind of a little bit painful. I'm writing A to this, A to this, A to this, A to this, A to this. It's a lot of redundancy in this notation. So we will simplify the notation a little bit, okay? And this is again standard. So if you see this from now on, it's the same thing in our definitions, but abbreviated. So if we have multiple rules, with same variable, we write them on a single line. Okay, I'll just give an example. Okay, so if I have something like A goes to Z1, A goes to Z2, A goes to Z3, instead of writing it 3 times, we will just write it once as A goes to Z1 or Z2 or Z3. Okay, and this slash is meant to denote, okay, or like, different rules. Technically, it is really 3 rules: A to Z1, A to Z2, A to Z3. We're just putting them under kind of one line to make it a little succincter. Okay, so in this notation, the old grammar would become something like this. So you have G2, which is just A, the terminals, the rules, starting symbol, and the rules are just A goes to 0A0, 1A1, 0 or 1 or epsilon. Okay, it's just shorthand for writing 5 different rules. The left hand side are all the same, so let's just put them together in one line. All right. Okay, let's do one more nice example. So far we've only been looking at things where kind of you only had one variable always, right? You had A, it went to 0A0. You had A, which went to 1A1, right? Now we'll do slightly more advanced stuff. So example, G3, and this has a start symbol S, again, a single variable. But now the alphabet is parenthesis, open parenthesis and close parenthesis, right? And the rules are going to be specified soon, and you have S, all right? And so sigma is just the parenthesis symbols. So you can imagine basically you're generating any sequence of, you're trying to generate. So the idea here is to generate valid parenthetical expressions. It's like this classic algorithmic or interview question, right? How would you recognize if a sequence of open and close parentheses is a valid expression, right? This is valid, whereas if I put something like this is not valid. Oh, well, this became valid. But let's say I do this. This is not valid, right? You can't match everything properly. Okay. And you can do this easily with a CFG. So the rules are, you can take S and go to something like this. Okay. It's a little bit like saying, if I have a valid expression, I can put 2 open and closed parentheses at the beginning, at the end, and it would still be valid. Or I can take any 2 valid expressions, put them next to each other, and that would still be valid. Or I can just replace it with epsilon. Okay. And if you try it out, you'll see that S implies star G3 of, I can do, well, let's do a couple of examples. I can go to this, right? And then I can go to just this guy. Okay. I can do maybe okay, I'm just giving some examples, right? And I'm replacing, okay, so here I'm replacing the first one, and here I'm replacing the second one. And then I can just replace the S's with epsilons, right? So I'll get okay. So what language does this grammar generate? Any guesses? So what's the grammar that you will get from this? Well, all strings of well-matched parentheses expressions. Okay. So if you think of mathematical expressions, then this grammar would generate all strings of well-matched parenthetical expressions. Any questions about this? Okay. So it's kind of nice to see that you can generate these kind of expressions with a concrete, like in almost 3 sets of rules, right? It's a very compact description of this entire language. Okay. And that's something very nice about context-free grammar. They can give you very compact, especially in the context of how important those languages are of those languages. Okay. So let me just say a few words about why we study CFGs. Okay. So the most important is the S to S rule, effectively a clean star operation. Yeah, that's actually a very good point. Like, if you have S to SS, it's almost like it lets you do like a clean star operation. You can concatenate things and so on. That's a very good abstraction of it. Okay. It gives you a nice shorthand way to do clean star. The power of clean star is already inbuilt into the language. Okay. That's kind of already a homework problem. The grammar, if the language is context-free, show that its clean star is context-free, you would do just this. Okay. All right. But we'll get to that later. So why context-free grammars? I would say the most important reason, they had their origins in linguistics, because initially people wanted to like codify, like, let's say actual spoken languages, right? Like, I'll say every sentence has like, noun, verb, object, action, and then you would like put some other rules and so on. That wasn't very successful. But for us as computer scientists, the reason they're so important is that they are what underlie programming languages. And not just 1 or 2 programming languages, all programming languages like, C, Java, Python, anything. At the end of the day, you come up with a grammar for it. You want to make a new language, you come up with a grammar for it. Rust, you come up with a grammar for it. Okay. So for all of these, there exists a grammar G that generates syntactically valid programs. Okay. Python is more forgiving, but you can imagine if you're writing some C program, you have an open parenthesis which is not matched with a closed parenthesis, you immediately get a syntax error, right? And the way those things are caught is basically by what we're going to see, like, by looking at the grammar and seeing if that string is in the grammar or not. Okay. So for every language, there is a grammar that generates syntactically valid programs. More concretely, for instance, there is a grammar, GPython. Okay. And this is explicitly written up somewhere, it's coded up in all kinds of Python compilers and interpreters, such that P is a valid program if and only if P is in the grammar of this program, is in the language of this grammar. Okay. And the grammar is pretty complicated. You have to come up with many, many rules, but once you come up with it, you have this very succinct way, compared to how complicated programs you can write. At the end of the day, the grammar, even if it's like, maybe hundreds of rules or even thousands of rules, it's still way simpler than the programs that you can actually have. Okay. And once you can have this, you can imagine the kinds of questions that we should be asking. If I write down if I tell you what are the rules of GPython, how does a Python compiler take a program or its purported program and tell me whether or not it's actually syntactically valid? If it is not syntactically valid, how does it identify the bugs in it and so on? Okay. But the starting point is to understand what these languages are. How do you check membership in a context-free grammar and other related questions around it? Okay. Any questions about the definition? Okay. So if there are no other questions about the definition, let's take a short break of 5 minutes. And when we come back, we will look at some other examples and compare them compare context-free grammars and their power and talk about designing context-free grammars. Okay, let's take a 5-minute break. Okay, so let's now, we have a new computational model, right? We have context-free grammars. And once you have a new computational model, we start asking questions about its power, right? How does it compare to the models that we already saw? It seems like, we saw 2 models already, which are regular languages or DFAs and also Turing machines. So let's compare them and see what happens, right? In some sense, we do think context-free grammars are maybe more powerful than DFAs, right? Because they are already able to generate things which DFS could not, right? Palindromes, 0 to the n, 1 to the n. We saw that they were not regular languages, but then they are context-free, okay? And this kind of leads to one of the questions that I just got asked. It wasn't a planted question, but we'll see that every regular language is also context-free. Okay, so every regular language is also context-free, meaning context-free languages or context-free grammars are actually strictly more powerful than DFAs. Okay, so you want to say that concretely for every DFA, there exists a context-free grammar G such that D of X equals FG of X for all X. Okay, so proof. So let me ask you first, but let's just set up some context, right? And you have a DFA which we think of as, recall, you have a transition function which tells you, okay, if you see some state from C, which is 0, 1 through C minus 1, and the symbol 0 or 1, you go to one of the states again. Okay, that's the complete description of the transition function. And then you have the set of accepting states. Okay. So for instance, you can imagine, maybe I have a finite automaton which looks like this. You start from 0, you see a 1, you go here, you see a 0, you stay there. You see a 1, you go here, you see a 0, you stay there. You see a 1, you go here, say a 0, you stay there. And let's say this is your accepting state. Okay, so this is a very concrete DFA. And now I want to build a grammar which is equivalent to this kind of stuff. Okay. Any suggestions or ideas on how I might build a grammar for a DFA? We want to do this in general, right? I give you any DFA, we want to build a grammar. But let's start with an example, like in even this DFA. Okay, it's kind of, so we want goal. We want a grammar G which has variables, alphabet, rules, and the start symbol, right? We say start. Okay. So there's a suggestion, make each state a variable, then a to 0, a and a to 1b, etc. Excellent suggestion. So let's try and formalize that, right? So if my DFA has C states, what I'm going to do is create a variable for each state. Okay, meaning I'll have v0, v1, v2, all the way up to vc minus 1. Okay, are the variables. Okay, so v is this guy. All right, and what should the terminals be? Well, we're interested in 0, 1, so the terminals should just be 0, 1. What should the starting variable be? Okay, what should the starting variable be? Well, it should correspond to the starting variable of our DFA, so v0. Okay, so we kind of specified 3 things, v, sigma, and the start. We have to tell what the rules are. Okay, so how about the rules? So idea 1, as was suggested here, and if you have a transition, which, if you're in state I, you read bit 0, you jump to state J, let's create a rule which captures this. Okay, so for each transition of the form T of I comma A is J, right? Meaning, if I'm in state I read bit A, I go to state J. That's what the DFA is doing, right? So we're thinking of the variable name is our proxy for what state the DFA is in. Okay, so we add a rule vi to a vj. Okay, so every time you read a bit and take a jump, we kind of codify it as an explicit rule. Okay, kind of a very simple grammar that you're getting, right? Every time the substitution is simple, that kind of, the new variable is always at the end of the string that you have on the right-hand side. All right, that's great. But then this by itself is not enough, right? If I only have these rules, I'll always have a variable on the right-hand side, right? Any derived string from a start will always have a variable. But I need to get rid of variables. How can I do that? Any suggestions? How can I get rid of variables? How can I finish the picture here? Empty string for accepting states, right? In a DFA, when you reach the end, when you reach an accepting state, that's when the string is in the language, right? So if you are in an accepting state, you can say, okay, now I'm going to I can, if I want to, get rid of this variable, okay? So for each accepting state, in the DFA, add the rule vi to epsilon. Okay, so that's it. That's a very simple construction. And let's kind of, maybe take this example and see it in action a little bit. Okay, so this is our example, DFA to CFG. Okay, so we have three variables. So I'm going to create three states. So we'll have three variables, V0, V1, V2. Okay, and what are the rules? Well, if I am at V0 and I see a 0, if I'm at state 0 and I see a 0, I go to, so T of 0, 0 is 0. T of 0, 1 is 1. Okay, so this leads to the rule V0, sorry. So this implies the rule V0 to 0 V0. This leads to the rule V0 to 1 V0. Okay, so so if I were to write it down succinctly, I'll say V0 to 0 V0 and 1 V1. Okay, so this should be 1, sorry. Okay, and V1 would be something similar, right? If you see a 0, you go to the same state, so the same variable. If you see a 1, you jump to 2, so you go to V2, right? V2 is 0 V2 and 1 V0. Okay, and finally, the only accept state is 0, so we add V0 to epsilon. Okay, so this right, so this grammar is equivalent to the DFA that we have. Right, start is V0, sigma is 0. Any questions about this conversion? Okay. So in conclusion, what we have is that summary context-free grammars are definitely at least as powerful as DFAs. Okay, but in fact, they're more powerful, right? Because they can recognize palindromes, which CFGs, which regular languages could not, right? CFGs are strictly more powerful than DFAs. Okay, so it's a stronger computational model than DFAs. Okay, Any questions? There's an excellent question here. Any direct conversions from regex or NFA to CFGs that are easily expressed, or should we really just do NFA to DFA and CFG? Okay. My claim is that if you have an NFA, converting it to a CFG is relatively straightforward. You don't have to go to you don't have to blow up the state space exponentially, go from NFA to DFA and then to CFG. Okay, so let me elaborate on that. You're taking away all my good homework questions. Okay, so question. So should I always do this conversion from an NFA to a DFA to a CFG, or can I do it directly? What do you think? Any suggestions? Okay, so I'll let you think about it, but as a hint, the main thing is when you think of an NFA, right? So let's say you have an NFA D, right? You have a transition function, you have a set of accepting states, and now the transition function is a little bit more complicated, right? You have C minus 1, you see a bit, which is like something, and then you output a set, right? So T of I comma A could be, maybe it's J1, J2, maybe JR. Okay, and let's say for the time being that there are no epsilon transitions. Okay, just imagine these are not there for the time being. Okay, so what would be a natural fix to do this, right? You're in an NFA, we're allowed to take all of these paths, and as long as one of them leads to an accept state, you're fine, right? And the thing I want to emphasize is that context-free grammars already have this branching kind of baked into the definition, right? I can just create multiple rules for each of these things. Okay, so if I were to convert an NFA to a CFG, what I can do is, I would add a rule which says VI to AVJ1, right? Or VI to AVJ2, and so on. Okay, so in NFA, you had to explore all of these branches in parallel. The same thing happens in context-free grammars, right? You can apply, you can choose which rule to apply. As long as that leads to your string, you're fine. It doesn't have to be a specific sequence of things. Okay. So for the conversion would be, the starting steps are the same, right? You'll have for the rules, for each rule VI to, for each transition, Okay, so once I do this, you would be fine. And these are the first set of rules, and then for each accepting state I in S, add rule VI. Okay, so even if you didn't know that NFS and DFS were equivalent, you can convert an NFA easily to a context-free grammar, and you can do this without like an exponential blow up in the kind of representation size. All right, any questions about this? Okay, so maybe let me also do an example conversion here, in the box. So example conversion of an NFA to a CFG. So let's say, my NFA is something like this. Okay, so, this is an NFA that we saw earlier, and it's an NFA because you can see there are two arrows with a 1, right? And you just do V0. So the variables are okay. Alphabet is 0, 1. Start is V0. And the rules are going to be V0 to 0 V0, right? Or 1 V0 and 1 V1. Okay, so that's it. So this is the main thing. Okay, so we have the non-determinism taken care of, and then everything else is kind of similar. Okay, so the last V4 is accepting state. So you have V4 epsilon. All of this is very good, but kind of this worked when we had no epsilon transitions. Okay, but what if you have epsilon transitions? How would you fix it? How would you add some new rules to kind of handle this scenario? Any suggestions? Imagine there was an epsilon transition from state I to state J. Like you went from state 1 to state 3 for free. How could you code it out? Yeah, Evan is absolutely right. You can just add a rule saying just jump from the variable corresponding to the origin of the epsilon state to the other variable. You're just jumping between variables. You're not adding or generating anything. Okay, so fix if you have a epsilon transition, from I to epsilon J, add rule vi to vj. That's it. Just jump between variables. You're not adding any literals, but you're kind of taking a parallel step. Okay. Any questions about this? Okay, so context-free grammars, quite powerful. They can seemingly do NFS also very easily. It's kind of baked into the definition. Okay. Now, often, sometimes when you have so much flexibility in designing the rules, we need to come up with some heuristics to guide our search for finding the right grammars. Okay, so let me give you some tips towards designing CFGs. Okay, this is something helpful, across many different areas. So the first thing, the first kind of simple tip is if you can break up the language into simpler pieces, then just do it. So break up the language L into simple pieces. Okay, imagine I come up and say, okay, here's a language. Can you design a CFG for it? We'll say, okay, maybe suppose I have a grammar G1, which generates language L1. Now I have a grammar G2, which generates language L2. Okay, my claim is then you can easily get a grammar which is for L1 union L2. How can I get a grammar for L1 union L2? Any suggestions? It's like kind of closure operations that we saw earlier, right? If I'm taking the union of the two languages, how can I create a new grammar which has this property? So let me give a hint. Maybe S1 is the start symbol for G1. Yeah, exactly, right? You can link up the start symbols easily. Kind of similar to what we did for NFAs, right? We created a new start state and had epsilon transitions. We're kind of doing something similar here. If S1 and S2 are the new start symbols for G1 and G2, I'm going to create a new start symbol S and a new rule, which is either go to S1 or go to S2. Okay. So now you kind of branched into L1 or L2, right? Now, once I go to S1, I'm following the exact same things to generate the strings in L1. Once I go to L2, S2, then I do all the things that I do for L2, right? So basically you have S, you can go to S1 and do G1 rules. S2, do G2 rules. Okay, and we can do it whichever way we want. So that's kind of the first tip. If you can break it up into simple pieces, then we can exploit it. All right. Tip 2, I think this is sort of very, or maybe one of the nicest things about context-free grammars is that context-free grammars can kind of a heuristic, right? So it's not formal description. So it can link strings. Okay. So meaning, think of the example of 0 to the n, 1 to the n. Right? So basically, we can say that for every 0, you insert a 1 around it. Okay, so you're linking or pairing up this 0 with this 1. In palindromes also, we did something similar. You go from A to 0, A 0. So you're linking like a 0 with a corresponding 0 on the other side. All right. Again, this is a heuristic. It's not like a rule, but it's something that you can potentially exploit if someone asks you to design context-free grammar for something. Okay. And the third tip, which is kind of what we already saw, is that regular languages are context-free. Okay. So, the best way to kind of go about designing context-free grammars is to really play around with them. And we'll see some examples next. But these guidelines are useful. If you break it up, you can break it up and try to design grammars for each individual one. You can pair up things cleverly if you want to. And then also the fact that all regular languages are context-free. Okay. So let's do some examples to kind of get some intuition, right? So here's a language, and I'm going to ask you to design a grammar for it. So the language I have is the following. I'll call it add and it contains all strings of the form 0 to the m, 1, 0 to the n, 1, 0 to the n plus. Okay, you have a string of zeros followed by a 1, you have a string of zeros followed by a 1, and then a string of the sum of the two strings, okay, of zeros. If you think about it, it somehow looks like this, right? Okay, so you have zeros, m of them, then you have a 1, and then you have zeros, n of them, then you have a 1, and then you have zeros, m plus n. Okay, and goal. Design a grammar for add. So I'm asking you to design me a grammar for addition. How can you do it? Any suggestions, ideas? Okay, let me give a hint. Right, so remember this thing about pairing up strings, right? Actually, let me write this as n plus m. So 0 to the m, 1. So one variable can be used to factor the outer shell of 0 to the m's, and the inner one is for something. Excellent. So basically, as we said, we can pair up bits, right? So let's think of it this way, right? I have this green chunk of zeros here. I'm going to pair them up with the last chunk of zeros. Yes, my drawing is kind of not very nice. Let's say this one is all the way here. And I have this, cyan chunk of blues, which I'll pair up with these guys. Okay, so idea as suggested in the chat here is you'll say to pair up the green zeros and oops. Pair up the cyan zeros. Okay, so you're going to first generate maybe the outer pieces and then the inner pieces. Okay, so let me write it down. So I'll have a rule to say A goes to 0, A, 0. Okay, so if I keep applying this rule, what I'll do is, I'll end up generating a bunch of zeros, okay, on the outside here, and a bunch of zeros on the right, but there's a middle piece A always. Okay, and then I'll switch tracks. I'll say go from A to 1 and B. Okay, so now I'm switching. I need to have a 1, which is kind of like a marker. And then I have to generate the cyan portion, right? Maybe let me say this is like go from A to 1B. And then I just do B goes to 0, B, 0. All right. So use this. And finally, you'll also have B goes to 1. So use this to generate green portion and use this to generate cyan portion. Okay, so your final grammar, for instance, you would say, okay, so why is this okay? So you'll say A can go to anything of the form 0 to the m, A 0 to the m. If I keep applying, why is it A to 1B instead of A to B? Yeah, so that's just because, we have to introduce, we have this kind of demarcating 1. So I'm adding the 1 there to kind of separate out the first chunk of zeros from the second chunk of zeros. Okay. So, I apply just the green rule again and again. I end up with a string like this. And now, if I apply the black rule, I'll end up with 1, B, and then 0 to the m. Okay. And now I keep applying the cyan rule. I'll get 0 to the m, 1, okay. So I'm always generating an equal number of zeros around the symbol B. That's what we're exploiting here, right? And then now you're basically done. I get this is just 0 to the m, 1, 0 to the n, 1, 0 to the n. Okay. So is this construction clear? Kind of, all we are doing is kind of pairing things up in a nice way. All right. So I can define the grammar as follows. Summary. So there are 2 variables now, A and B. The terminals are just 0, 1. Start is A. And the rules are still fairly simple. A goes to 0, A, 0, 1, B. And B goes to 0, B, 0, and 1. Okay, so we kind of only have 4 rules, and it almost seems like we're able to do addition now. Okay, kind of if your things are encoded in unary, you can check for proper addition, which is cool. It's kind of a simple thing. Let's do one more puzzle. And this is from the exam. So let's say L equals all x. X is of even length. Middle two symbols are same. Okay, in the exam, you showed that this is not a regular language, but now I'm asking you to show that this is a context-free language. How can I generate this? So think about it like, from these tips, right? We can break it up into pieces. So what is this language? You are to look at all strings where even length. So if you break it up into two equal pieces, then the middle two symbols are the same. Like, they're either 0, 0, or you need to have 1, 1. And whatever comes in the remaining doesn't matter as long as they're the same length. Okay, so same length. Okay, so what would be a grammar which can generate such a thing? Any suggestions? Maybe let me ask an easier question. What's a grammar to generate strings of even length only? Now I ask you, okay, only generate even length. Actually, someone gave us the full answer. So, so the idea is to really, we had to pair up the lengths of these things, right? We don't have to pair up much, just the lengths. Meaning every time I create a symbol to the left, I should also create a symbol to the right. Every time I create a symbol to the right, I should also create a symbol to the left. But they don't have to match, right? So to make the lengths of the two pieces equal, I'll say A goes to 0, A 0. Or, I can go to 0, A 1, or to 1, A 0, or 1, A 1. Okay. So this ensures that the string to the left of A, the number of terminals you generate, and the number of terminals to the right are of the same length. Okay, they need not match. They can be arbitrary strings of zeros and ones, but then that's fine. Now, finally, we had to add in the same middle symbol. How can I do that? Well, once I come this far, I could just replace this A directly with 0, 0 or 1, 1. Again, this is exactly the suggestion by Minghao Shen. So, that's all there is to this particular language. Okay, so let me say generates equal length terminal strings on both sides of A. Okay. And, just for, let's assume that epsilon is not. Again, this is kind of a minor annoyance. So let's assume that the empty string is not in this language. If it is, you would just create a new symbol, add it in. So it's not a big deal. Okay. Let's not spoil the elegance by doing something like that. Okay. Let's do one more example to kind of get the full hang of it. And something similar, but slightly different. So X is of odd length, but the first, middle, and end symbols are the same. Okay, we're just kind of doing doing a few examples to understand the definitions. Playing with these examples is mainly to understand the definitions and kind of get us familiar with the rules of context-free grammars, right? We'll start asking about deeper questions, more useful from a practical standpoint questions in the next lecture. But right now our focus is to kind of understand the definitions, right? So there's a question by Richard here, which is, what would you do if you had to add the empty string? Well, to add empty string to the language, I'll say create a new start symbol S and say S goes to A/epsilon, and then A goes to all of these things. Okay, so I kind of added epsilon by brute force in some sense. You can, starting from the start, you just go to epsilon and that's it. Or you go back to your old grammar. Okay. All right. So now, I ask you something seemingly a bit more complicated, which is, odd length, first, middle, and end symbols are the same, right? Meaning I have one, let's say 0, 1, 0, maybe 1, 0, 1, 0, and 1. Okay. So it's odd length, and the middle and starting symbols are the same, right? So you can also have 0, maybe 1, 1, 1, 0. Actually, this might give a wrong impression. So let me change it to 1, 0, 1, and 0, 1, 0, and 0. Okay. The only things that need to match are the starting, middle, and ending symbols. How can I get a grammar for this? Okay, there's a suggestion A to 0 be 0, or to 1 be 1, B to 0 be 0. Let me understand. I think there may be a problem here, because if you go to, so for the suggestion in the chat, you might end up getting like, A to, yeah, it doesn't match middle exactly, Luca. So you might not match the middle portion, which is a bit difficult, right? So there's another suggestion, we might need to split the B into 2 other states so that we can't get to 0, 1, 0 and 1, 0, 1. Exactly, right? And conceptually, we are using tip number 1, which is if I can break up the language into 2 pieces, then do that first and design languages, design grammars for each piece. Okay. I can imagine there being 2 languages here, L1, let's say, is X odd length start and middle equal 1. Okay, so kind of, there are 2 kinds of strings. All strings where the start, middle, and end are exactly 1. All things where the start, middle, and end are zeros. Right, so let me just do them both separately. So that way I don't have to mix and match the middle symbol, right? Maybe L0 is all X odd length start and comma middle equals 0. Okay, and the language we are interested in is exactly the union of these 2 things. All right, and once I get here, Luca's suggestion works perfectly, right? So I can say, you go from for, let's say, L0, I can design a grammar I'll get to that question in a second, but let me finish this. I can go from A to 0, A, 0, right? Or and then I can go to 0, A, well, okay. Hold on. Maybe maybe let me build it off of this suggestion here. So let's say I go to 0, B, 0, right? And well, no, let me just do this. Right, so I want to say you're kind of generating these two things, right? First, so I go to 0, A, 0. I mean, the first thing is do this. I've generated the starting and end pieces. Okay, and now I say B goes to 0, B, 0, or to 0, B, 1, or to 1, B, 0, or to 1, B, 1. Okay. So what we are saying is, okay, this piece, starting and end symbols are same. We explicitly generated them. And now I need the length of whatever occurs before the quote unquote middle symbol to be different, to be the same. Okay. So when I do this, basically what happened is I generate a 0 and 0, and then I have B. I can generate anything which is the same length on both sides of B. Okay, and then I have to go from B to 0. All right, any questions? And again, there's one border case, which is if I just have the string 0, one could argue that the start, middle, and end are the same because it's a single bit 0, but just hard code it. Okay, so to capture just 0. Okay, does this construction make sense? Right, so we're kind of following the same logic, which is, I put the first and end symbols first, and then generate the equal length pieces in front of and to the right, to the left and right of B, and then make B to be 0. Okay. And for L1, I will say something similar, but maybe with new variables, 1D1 or 1. Then D goes to 0D0, 0D1, 1D0, 1D1, and 1. All right. And for L, we will say, your variables will be S, which is going to be a new thing, A, B, C, D. Start is S. And I will add rules of L0, rules of L1, plus S goes to A or C. Okay. So breaking it up into two of these pieces gave us this flexibility to kind of study each one and design languages for each one separate. All right. And there's a question here, but if you keep splitting states to remember a bit selected, then the number of rules can explode with the number of bits you're remembering. That is true, but here we are kind of only have two cases, so that's why it's fun, right? We only have a case where the middle, it's only either they all match 0 or they all match 1. If it's something more complicated, then it will have to grow. All right. Okay. So we saw some, kind of definition and kind of got some intuition for playing around with the definition by looking at some examples. and had some fun designing grammars, right? So in the next lecture, we'll start asking about more conceptually important and practically important questions. Okay, if I have a grammar, how do I derive string? How do I know if a string can be derived in an algorithmic way? Can I answer meta questions about grammars? Okay, that was one of the main reasons we motivated defining grammars. Okay, so we'll talk about all of those things on Monday. All right. So thanks everyone, and I'll see you on Monday.